Hi, everybody. I'm Benji Koshi with Minnesota Institute for Astrophysics, and I am so glad to see you all here. Just want to welcome you tonight. Many of you, if not all of you, I got a yellow slip of paper that's for feedback, some ideas for future events, and sign up for our mailing list if you haven't already. After the lecture, there will be a Q&A period. So if you have questions, just flag somebody down who has a microphone, and they'll get you that so you can ask your questions. And next up, we've got Director of MIfA, Claudia Scarlata. And so here's Claudia.
So good evening, everyone. Can you hear me? Almost. So welcome, everyone. This is the 13th public lecture of the Minnesota Institute for Astrophysics. We have been doing it for 10 years now. And the goal of this lecture is to bring to the Minneapolis community the great research that the member of our institute conduct. So we want to try and make it accessible to everyone and try and inspire you to this universe, to learn more about this universe in which we live in. So today is my pleasure to introduce tonight's speaker, Professor Keith Olive. Professor Olive is a member of the Minnesota Institute of Astrophysics, as well as of the Fine Institute for Theoretical Physics in the School of Physics and Astronomy. Dr. Olive is a McKnight Distinguished Professor and currently holds the Lupkin Chair in Theoretical Physics. Dr. Olive got his master's and bachelor degree at the same time in 1978 in physics from University of Chicago, as well as 3 years after, still from University of Chicago, his PhD in physics. Then he went on to do some research at Fermilab, Harvard, and CERN. And then we were lucky to capture him in 1985, and he has been at the at the University of Minnesota since then. So Dr. Olive's his research contribution received a large number of awards, is widely recognized. He earned the National Science Foundation Young Investigator Award from 1987 to 1994. He was elected a Fellow of the American Physical Society in 2003. It's a long list. And then he received the Hans Bethe Prize in 2018, as well as the George Ward Taylor Award for Distinguished Research from the College of Science and Engineering here at the University of Minnesota. His research explores some of the most fundamental questions in particle physics and cosmology. His contributions are well known, particularly for Big Bang nucleosynthesis, dark matter, as well as inflation. And this is work that lies at the heart of cosmology as well as astroparticle physics. So welcome. Please join me in welcoming Professor Olive. Thank you.
Okay, well, thank you, Claudia, and good evening, everybody. I'm very happy to be able to tell you about some of the things that I think about from day to day. You might have noticed, if you really paid attention, I changed slightly the title. It's a journey from the origin of time, and so I thought I was going to go more in chronological order. After a little bit of an introduction, then we're going to go back to the very earliest moments of the universe as we know them today. The field is cosmology, and cosmology refers to how we describe the universe today and how it evolved to the universe today. Because what I'll be talking about in terms of the very early universe, and I'll tell you what I mean by that, having an understanding of the fundamental forces in nature and the particles in nature are critical, because that's what set everything up to be able to get to the point that we are today. And so mainly I'll be talking about the first 3 minutes or so, and you might think that's a short time. I don't mean to disappoint you, but that's a very long time. And so we will see what I mean by that. So just the very basics, and we're going to have to spend a little bit of time understanding what some of these things mean. The universe is about 13.8 billion years old. So GYR is the G is for billion. That's supposedly taking us from, if you want, the moment of the Big Bang to the present day. The universe is expanding, and that's a concept that you think you might understand. Maybe some of you, I'm sure, do. But we have to understand what that actually means for a universe or a space to be expanding. It's maybe not exactly what you think it is. What we know now, in addition, is that expansion is actually accelerating. And so that, of course, has very profound consequences on the future. Two things that are critical for our understanding of the universe is that the universe is both homogeneous and isotropic, and I'll say a little bit more about that, but basically it means it's very smooth on very large distance scales, and no matter which direction you look, it looks more or less the same. So just sort of the quick summary so you have an idea of where we're going. The idea of the early universe is that it was not filled with stars and planets and galaxies. It was actually filled with particles, very, very energetic particles. So they were very hot, and the density was very large, so even much hotter and denser than, say, the center of a star. And so you had this plasma of particles and radiation. And by radiation, I'll use that term a few times. It doesn't mean the radiation in terms of the medical sense or the nuclear sense. The radiation here just means that they're very energetic particles. Whenever a particle is very, very energetic, we refer to it as radiation. So as the universe is expanding, it's going to start cooling. And from that very hot and dense state, we eventually form some of the light nuclei, like helium, and then eventually we form neutral atoms, and then later on, those will go on and be able to form stars and galaxies. Now, another thing that happened, now this is now in the very extremely early universe, when the expansion was extremely rapid, there were some inhomogeneities present. They were very tiny, but there were some inhomogeneities there. And those eventually began to grow. And those inhomogeneities, which are calculable, eventually become dominated by dark matter. And I won't talk too much about dark matter today. I'll say something about it a little bit later towards the end, is that most of what I'm going to be talking about, the dark matter, isn't important. In fact, most of the matter isn't even important. But these little inhomogeneities eventually grew and became what we see today as galaxies and clusters of galaxies. And only fairly recently has the universe, the expansion, started to accelerate and is dominated by something called dark energy, and I'll say a little bit about that as we go along as well. So just to get a little bit in the mood, we just can look at a few pretty pictures, because everybody likes to look at pretty pictures of the universe. This is a James Webb Telescope deep field image. Sort of interesting. I'll say a little bit more about the galaxy that's up there that looks a little bit like a question mark. I think maybe from your perspective it looks like that. It's actually a multiple image of a galaxy that's some 5 billion light years away from us. And so it's sort of, and most of the things that you see there are not stars, but are actually galaxies. Oh, so now we see my cursor. Okay. This is an image of our sky, the full sky, and this is taken by, it's a combination of information from a Planck satellite and a Gaia satellite. The white that you're seeing there is basically the accumulated light coming from stars in our galaxy. The horizontal strip in the center is our galaxy. So this is in what we would call galactic coordinates. So everything is based on where our galaxy is and then looking at the sky around. The white cloudy stuff is basically dust that's in the way of everything. You see a little green patch, and I'm just going to show a few pictures. That green patch is actually very recent. I think it was only released about a month ago, maybe even actually a little less than a month ago, from the Euclid satellite. And this is quite interesting, well, quite remarkable. This is not what I do, but I'm fascinated, probably just as all of you are, by what they can do. So that's the little patch of the sky that they were looking at. And they're going to zoom in on smaller and smaller patches. The moon there is what the moon would look like in the sky on this kind of a patchwork. When you blow it up 3 times, you get this picture. And okay, it's nice. You blow it up again. Now you start seeing things. These are very, very distant. You can see from above where actually these things are sitting. You see a galaxy sort of in the middle, a little bit to the left. That galaxy is about 25 million light years away, which is actually close by. You see a string of sort of greenish orange. Sorry, I'm not going to be very good with colors, but the greenish orange, like a little line, that's a cluster of galaxies. And that cluster of galaxies is about 800 million light years away. Here's a blow-up of that. So now you see them more clearly, and you see a pair of galaxies. They're actually interacting with each other, sort of a little bit to the left of that. And they're about 500 million light years away. You blow it up again, and then you see them much more clearly, and you blow it up again, and you see this picture of a galaxy that, as I say, 500 million light years away. To see this with this kind of resolution, to me, is remarkable. But that's, as I say, things that the technology that goes into these things amazes me. All right, so now we can get down to business a little bit. And so we had the nice relaxing look at pictures. Now I'm going to have to put you a little bit out of your comfort zone and think a little bit. This is a picture of the history of the universe. You see from the Big Bang to the present day. This picture is one that you might have seen. It's often shown particularly by people doing cosmology from the astrophysics side. You see on the left, there's like a disk. That disk corresponds to the last surface where the microwave background was released. I'll explain all of that more later, but that's at about 300, 400,000 years after the Big Bang. And then you see everything else comes after that. So there's a period, here it's labeled as dark ages because there's no stars yet. Stars hadn't been born. You have the first stars forming, and then eventually galaxies, cluster galaxies, and eventually you get to today, and then you see this accelerated expansion. What I'm going to be talking about is everything to the left of that disk, okay? And it's not as pretty as a picture, but there's a lot of information in this plot, and I'm going to be showing this plot over and over again. So you don't have to get it all now. You'll come back to it. But as an introduction to this plot, you see this diagonal here. There's 3 quantities that are shown. The top line is the time in seconds, and except at the right it's at years. So you have today corresponding to this 13.8 billion years, and then going back, I don't have a pointer, so I don't. The line that's here that says cosmic microwave radiation visible, that's at 300,000 years. That was that disk that I showed on the previous slide. And so we're going to be talking about everything else to the right. And you see, basically, it's filled with particles. Sometimes they're free particles. They have little squiggles, which is the radiation. And you have sometimes they're bound up. And so we'll be talking a little bit about all these various stages here. The second line is the temperature, and the temperature in units of Kelvin. When you get to the really high temperatures, the units don't matter that much. But you see, today the temperature of the universe is about 3 degrees Kelvin. So Kelvin is absolute 0. 0 Celsius is at 273 degrees Kelvin. And so you see, you go back in time, you get to 15 Kelvin. 3,000 is 3,000 degrees is a little bit, it's close to the temperature near the surface of the sun. Not quite. 1 billion degrees is the next division. That's sort of the temperature in the center of the sun. And then you go up to much higher temperatures, 10 to the 12, which is 1 trillion degrees, and then 10 to the 15, and then 10 to the 28, 10 to the 32. The bottom line is the energy associated with that temperature. So that's typical energy of particles. And the units here are GeV. And so the G, again, is 1 billion. The EV is corresponding to what's called an electron volt. And the electron volt is the energy, say, if you have 2 plates with 1 volt across them and you put an electron and it accelerates to the other plate, it'll pick up an energy of 1 electron volt. And so if another way to think about it, you've all heard of E equals mc squared, so you can transfer a mass into a unit of energy. The mass of a single proton is 1 GeV, roughly 1 GeV, and so that tells you what a GeV is in terms of energy. If you can convert all of the energy of the mass of a proton into energy, you would get 1 GeV. Okay, so we need to understand what's going on in the universe. It really starts with gravity. And for the most part, we have Newton's gravity, Newton's laws, which are great for solving things like the motions of projectiles or the motions of planets and things like that. It works very well, but eventually it breaks down. And eventually you need general relativity, so Einstein's theory, which is a correction to Newtonian gravity. So Newtonian gravity is an approximation to general relativity. But for relativity, you need a theory, well, it is a theory of what's called curved space-time. And so that's a notion that we have to get through, is what does it mean for space-time to be curved? Because I think all of you would think it's flat, right? It seems flat. I mean, we don't even have a real good concept of what it means for space to be curved, certainly not from our daily experiences. So let's try and take it a little bit step by step. So here's a circle, and you would say, well, the circle looks like it's curved. Well, the space appears flat, and it's a little bit a product of our environment, of how we are relative to the space. So if you look at a little segment of that circle, you can see it's not perfect there, but it's okay. And you take that away so you can see it. It's almost straight. It's almost a little straight line. If you go to very, very small arcs, they would appear straight. The smaller you are relative to the circle, the flatter the circle starts to look. So the only way that you see that the circle is actually curved is to be able to step outside the circle. So that means here, I put the circle on a plane, right? It's very hard to imagine a circle not on a plane, right? You have to think about yourself being on that circle, going around one way or the other, but that's all you can do. You can't move off the circle. And so to see that it's curved, if you go off the circle, then you see, oh, I put it on a plane, I see it's obviously curved, right? Or if I'm able to really go around, say I go all the way around and I come back to where I started from, then I say, oh, it must be curved. This is not a good example because the circle is actually flat, because if I cut it, I can straighten it out. So that's not the best example. So let's go to the one where we're talking about a sphere. So now again, we're thinking we're on the sphere, the Earth, if you want, but we can't go off it. We can't go in it, we can't go off it. We're confined to that surface. And as you know, people thought for hundreds, I don't know, 1,000 years, that the Earth was flat, right? Because it looks flat. When you look out, it appears to be flat. It's only if you can get off the Earth from a distance, then you see, oh, it's a sphere, right? But that requires you getting off of it, which if I say you're confined to that sphere, you can't do it. Or you can sample large distances. So you can get in a boat and go all the way around the Earth, and then you find, oh, I can get back to where I started. It must be curved, right? Now, there's some things you know from experience, I'm sure, that straight lines, how straight lines work in curved space. So if you've ever flown from Minneapolis to Paris, you'll notice that the plane takes this kind of trajectory. And maybe you ask the question, why doesn't it do that? Well, this is a projection onto a flat surface, which the Earth is not flat. So if you look at it another way, what the plane is doing is actually flying a straight line along what's called a great circle or a geodesic. So a geodesic is always the shortest distance between 2 points, and so the plane is flying along a geodesic, which is the straight line on a curved surface. The straight line on the flat surface is the black one below. So in the universe, when we're talking about three-dimensional space, now we have the extra problem, because to understand the curvature of the three-dimensional space, it would be ideal if we can get out of that space and maybe into a fourth dimension, fourth spatial dimension. We obviously can't do that. We have no idea how to do that. Our brains aren't even wired to think that way of how we're going to get out of the three dimensions to be able to see the curvature. But you can sample large distances, and this was one of the ways that general relativity was proven in the early parts of the 20th century, and that was to look at the bending of light around the sun. So here the experiment was that, well, you know the position of stars, say during the night, and you know how they are traveling during the different times of the year. And then during an eclipse, what Einstein did is he had an experiment looking for a star where he knew the position of the star, but found that it was in a different place. So our eyes, our brains tell us that the position of the star is traveling, the light coming from that star is coming along a straight line. And in fact, but we know that the star is actually somewhere else, and that proved that the light got bent, in our minds, got bent around the sun, because what the sun is doing is actually curving the space in its proximity. And then, of course, the angle that's predicted in general relativity is what was discovered. So you can think on much larger scales, because there's not the sun bending the space right near the sun is not that dramatic from a cosmological point of view. But you can imagine now setting up something like an optical table here, where you have us on the right, bottom right, and you're looking at some galaxy far into the distance. But in the meantime, there's a cluster of galaxies in the middle, and what's happening now is that the light is getting bent around that cluster, so that cluster is providing some sort of curvature for the space, but now on a much larger scale. And what's going to happen is you're going to eventually see multiple images. This is, of course, exaggerated, but you can now, from what we're looking at, if you go back and you look at what you think are straight lines, you would say that that galaxy in the background is sitting there at many different places. In fact, you can rotate this around, and you would expect it to be in a ring. This is actually a fairly old picture, some 20 years ago, I believe. Maybe even more than that. Maybe it's probably getting close to 30 years ago. This picture was taken. And here you see in the front a cluster of galaxies, and the blue galaxy in the back, you see there's a few of them, and they're forming sort of a ring shape. It's not actually distinct galaxies. Those are different images, multiple images of exactly the same galaxy, which is being lensed by the curvature of space. And this thing is about 5 billion light years away. Here's another one where you see really very clearly the curvature, the bending of this galaxy, its image getting spread out. This one, the lens, the bright spot in the middle, is about 5 billion light years away. The galaxy behind it is about 19 billion light years away. I want you to think about that. I told you the age of the universe was 13 billion years, but that galaxy is 19 billion light years away. I'm not going to tell you the answer now, but I'll let you think about that. Here's another image with a nice arc. This one is really cool because you see there are 3 little dots. It's blown up here. The 3 little dots are supernova, and now you have multiple images of a supernova going off in this lensed image. And they actually represent different times at which the supernova in which you're looking at. They're not identical snapshots. This is something that Pat Kelly here at the Minnesota Institute for Astrophysics is really an expert on. All right, isotropy and homogeneity. Okay, this is the simple picture. You have the homogeneity, as I said, the universe is very smooth on very, very large scales. It's clearly not completely homogeneous because we have stars, we have galaxies, we have clusters of galaxies. The density of matter inside a galaxy is far greater than the density of matter outside the galaxy. So you have to do some kind of averaging. And if you go on to large enough distance scales, then it appears that the universe is actually quite homogeneous. And isotropic, well, if you look in all the different directions, more or less it's always going to be about the same. And you can quantify that. And the best way to do that is from the microwave background. And this is a temperature map, and I'll come back to what this really is later on. This is a temperature map of the sky. I already said that the temperature, the overall temperature is about 3 degrees. This is telling you something about the differences in temperature in different directions. So this is the same kind of map I showed you before. The galaxy is sitting in the middle. That's been taken out so we can see the microwave background there. But you see the difference between blue and red there is, you know, only a few hundred microkelvin, right? The temperature overall is about 3 Kelvin, and the differences. So it's pretty smooth. It's not perfectly smooth. It's pretty smooth. So what are the consequences of homogeneity and isotropy? Well, it tells you that the universe expands or contracts. Those are really the only two choices. When Einstein discovered this, from the theory of relativity, he also had then immediately a cosmological model. And he wasn't aware that there was actually data that the universe is expanding. So this bothered him, and he thought, well, my theory can't be wrong, so there's got to be some way to fix it. And he knew it was also that the theory was based on differential equations in which you have to integrate. And if you know your calculus, you know when you integrate something, you get a constant of integration, which you're free to do with what you want. And so he found that if he has this constant, he could set it so that the universe was exactly static. It's just sitting still. I'm sure he knew better that this is not a good solution. It's tuned, and it's not even stable, but nevertheless, it was a possibility. He then retracted it, of course, once it became widely known that the universe was expanding, but we'll come back to that as well. So the expansion leads to Hubble's law, and Hubble's law just tells you that the velocity of a distant object receding from us is proportional to its distance, and the constant of proportionality is sometimes called Hubble's constant or Hubble's parameter, because it's actually changing. So Hubble measured the velocity as a function to the distance. The velocity you get from something called a redshift. So when something is moving away from you, the light coming from that gets stretched out a little bit so it appears a little redder than it should be. And by seeing how much redder it is, you find out the velocity. And the units here are, if you can see it, it's kilometers per second. So you see that these things are really moving away fast in thousands of kilometers per second. And the distance here is in megaparsecs. A parsec is about 3 light years, so a megaparsec is about 3 million light years. And indeed, it's a straight line, so you have Hubble's law. It actually breaks down at very large distances. So what does it mean that the universe is expanding? So let's start with flat space. Space can be flat. It doesn't have to be curved on large scales. In fact, observations tell us that it is actually quite flat. But flat space can expand even though the volume is infinite. So it could be that the universe is infinite and flat and expanding. And you might think, well, what's it expanding into? That's the first question you hear. What is it expanding into? It's not. It's not expanding into anything. Things are moving apart in space, but they're not moving relative to the space. So what do I mean by that? So here, again, it's easier in 2 dimensions. So we'll put a plane down here. We'll have these Go chips as galaxies, and they're somewhat distant from each other. And the universe, there's no center, so this is an infinite plane. There's no center to this plane, but it's expanding. It's just getting bigger. And the chips are moving away from each other. Galaxies are moving away from each other, but their coordinates aren't changing. They're not moving relative to the coordinate system. They're just moving away from each other as the space is expanding. Okay? There's no center, right? And it's expanding, and it's infinite. It may be easier on a curved, closed space. So there the volume is finite. So I'm going to show you, again, 2-dimensional, so the volume means now the surface area. So the surface area is finite. Okay, now as you blow it up, it's getting bigger. and the galaxies, again, on fixed coordinates, now latitude, longitude, if you want, are getting farther and farther away from each other. Okay? Each point sees every other point moving away from itself. Right? So no, there is no center. Don't think about the center of the sphere, right? Because that's in the 3 space. That's not, you're not allowed to go there. You have to be confined to the surface, and there's no center to that surface. Okay. So we have homogeneity, isotropy. We have an expanding universe. Hubble actually first measured it to be, this is the units for that parameter. It's 500 kilometers per second per megaparsec. Seems a little bit funny, but what it means is if you put something at, say, a megaparsec away from you, it will be moving at a velocity of 500 kilometers per second. So that's how to interpret that. The trouble is that the Hubble parameter actually is related to the age of the universe. Actually, 1 over the Hubble parameter, you have to convert the units, but the 1 over the Hubble parameter is related to the age of the universe, and that would say that the universe was about 1 to 2 billion years old. Okay, that's not good because it was known already that the Earth is older than that. So there's an inconsistency, and immediately then you get competing theories. Okay, now we know that that measurement was off. Its best number today is around 70. There's a little bit of dispute on that, but I'm not going to go into that. But so the inconsistency, there was for a long time, and this is a long time meaning from somewhere around the 40s to the 60s, 1940s to 1960s, there were 2 sort of competing models of cosmology. There was the steady state theory, which was mainly promoted by Fred Hoyle and some of his colleagues, and the Big Bang theory, which was promoted by George Gamow and his colleagues. Hoyle actually named Gamow's theory, the Big Bang theory, actually to make it sound silly. He thought, well, that's the way to put your competitors down, just make them sound silly. So who would believe in a Big Bang theory when I've got a steady state theory? Steady state sounds very scientific. It must be true. Steady state theory is one where the universe is expanding always, and things are getting farther apart, but new things are being born in between, and so on average things always look the same. So if the normal homogeneity and isotropy relate to what's sometimes called the cosmological principle, steady state theory, they said, was the perfect cosmological principle. Now, with any good scientific theory, you want to be able to test it and either verify it to the extent that you can or falsify it. And in 1964, when the microwave background, or this 3-degree background, was discovered, it immediately falsified the steady state universe because there was no such background in that theory. And immediately, the Big Bang theory was promoted as now the leading cosmological theory. So let's go back to this picture here. And now we're going to go and try and talk about the very early portions of this. So when I was in graduate school, I had a friend who, he'd ask me, what is it that you do? And at that point, okay, we're out at lunch or whatever, and I'm trying to, I said, well, I work on the embarrassingly early universe. And by that, I meant talking about times that are 10 to the minus 36 seconds. And there's numerically what that means. It's 35 zeros after the decimal point with a 1. For reference there, you can see how much smaller that is than a nanosecond, 10 to the minus 9 seconds, or an attosecond, which has gotten some attention more recently because that corresponds to light travel time within atomic scales, and that got a Nobel Prize just recently. But here we're talking about timescales which are significantly smaller than that. All right, t equals to 0. What does that mean? Let me go back here. So you might be disappointed. There's a question mark there at the Big Bang, right? Because we don't really know. Sorry, but we don't really know. And the problem with that is, well, okay, in Einstein's theory of relativity, the volume of space is going to 0. Okay, again, hard concept when you think that it's infinite, but it's going to 0. Okay, something's not quite right. You should also not think about when the universe was, if you want to say, created in the Big Bang, it happened somewhere. It didn't happen somewhere, it happened everywhere. right? All of space was created, and so there's not like some place out in the universe where we say, this is it, this is where it started. No, it happened everywhere at once. The density goes to infinity, and gravity gets strong, and that means that we probably need a quantum theory of gravity. You know, maybe that's string theory. That's something we don't fully understand yet. Okay. So how does that all relate to particles? So now we're going to have to put in particles and interactions. And so there are 4 fundamental forces. Okay, you're counting them, you see 5. But electricity and magnetism, really known since the 1800s to be the same, different manifestations of the same thing. That was known already from Maxwell. And then we got a full quantum theory of electromagnetism from Feynman in the 1930s. There's the weak nuclear force that's, if you want in simple terms, responsible for radioactivity, fission, breaking up of nuclei. The strong nuclear force, the opposite, fusion, it's what holds nuclei together. And then, of course, gravity. For the weak force, I put a picture of Enrico Fermi, who is largely responsible for developing that also in the 1930s. Steven Weinberg, who is largely responsible for the unification of the weak and electromagnetic forces in the 1960s. Gell-Mann first proposed a quark theory for the strong interactions, and in the 1970s there were attempts to unify the electroweak force with the strong force. Now, the electroweak interaction as a unified theory is extremely well tested, almost disappointingly well tested, because that's what's being done at accelerators. And for example, at LHC, there was the discovery of the Higgs boson. This theory is amazingly robust. And of course, as a theorist, you're always looking for something new, and they're not finding anything new. They're just testing that this is such an accurate theory. That's why I say it's a little bit disappointing. So that is very well established. Grand unified theories has not been established. It's sort of in the same vein. It makes sense. There are experimental tests of it. They're very difficult tests. And I'll come back to one of them later on. But that is not proven. There's been no evidence directly for grand unification. And string theory is even harder. So that's really started in the 1980s. That's an attempt to unify gravity with the other interactions. And as you can imagine, since it's a correction to general relativity, so string theory should have general relativity as an approximation, just like relativity had Newtonian theory as an approximation. But so there's certainly no tests of that. All right, what kind of expansion can we have? Now we're going to really get into some things here. So if the universe early on was, I said, dominated by radiation, so very, very hot, fast particles. The universe expands as a power law, t to the 1/2 is square root of t. So it's just moving along nicely. When it becomes dominated by slow matter, or dust we call it sometimes, just low energy particles, it's still going as a power law. The power changes. Okay, that's not a big deal. That's important, but it's not a big deal. What about when it's vacuum dominated? Then all of a sudden it looks like the universe is expanding exponentially. But now you're going to tell me, what do you mean by vacuum dominated? Because your idea of the vacuum is that there's nothing there. So if there's nothing there, how can it dominate over anything? So what we mean by vacuum is not just the absence of particles. What we mean by a vacuum is the state of the theory, if you want, where if you put something in the vacuum, it will have a very definite type of interaction. So if we put, say, an electron into one vacuum, it might have no mass and have very different interactions than if we put it in another vacuum where it does have a mass and, say, interacts with the Higgs boson and has all kinds of other interactions. So our concept of vacuum is a little bit different than what the terminology means in everyday life. And as I say, this leads to exponential expansion. But so I tried to explain a little bit, what does this mean? And this is probably the most complicated thing I'm going to show you tonight. So after you get through this, you're going to be fine. This is a picture of what's called a cosmological phase transition. what's on the vertical scale here is some energy. Okay, it's actually an energy density. It's the amount of energy per cubic centimeter, if you want. The other scale is just telling you something about that you have one vacuum or another. So the universe wants to be in a minimum. Things like to be in the lowest energy state if possible. Okay, that's, I think, easy to understand. And here on the one side, on the left, the universe wants to be in this grand unified theory. And in the grand unified theory, all the interactions are unified except for gravity. Everything is okay, you have that. But we live in the other one, is what we call here the standard model. And so that's the vacuum. So each of these minima correspond to what we call vacua. If the universe gets trapped in one vacua, it eventually has to get to another, but there's a barrier. Now, classically, if you put like a little ball in there, so if you put the ball somewhere, it'll always roll, it'll roll into the minimum. But if it rolls into the minimum that's all the way to the left, classically it would get stuck. And you would be always in this grand unified phase. Well, okay, except quantum mechanically, there is a chance that it jumps from one minimum to the other. And how that happens is through what we call a formation of a bubble. Now that might seem strange because I'm saying it that way, but it's actually quite common. And there's a phase transition that you're all very aware of, and that's boiling water, the transition from a liquid to a gas. When you start water boiling, what do? You form bubbles. I mean, usually you form them around the edges, but that's a different effect. If you had a really big vat and you had a way of uniformly heating the water, bubbles would form everywhere throughout the water. And then eventually they would start growing, and you'd have lots of bubbles, and they would all start merging, and you would turn all of your water into steam. Okay. So the same thing happening here. We've got nothing in the universe, it's vacuum, and you form a bubble. And inside the bubble is the other vacuum. Okay? There is some energy density associated with the wall of the bubble, because that's the energy that's different from these two sides. So the idea here is that to have a transition in the early universe, you might form bubbles. It doesn't have to be this way. There are other ways to have phase transitions. This is what's called a first-order phase transition. You have to then form bubbles, and they eventually merge, and you recover the universe in another state. If you're stuck in the other state, this energy is like a constant. It's a constant energy, and that's what causes this exponential expansion. And that's what was the basis of the theory of inflation, which was developed by Alan Guth in around 1982. There are other ideas floating around at the time very close to it. So what were the reasons for thinking about this kind of transition in this context? So remember, we're here at the very, very early stages. 10 to the minus 36 seconds is when this all is going to start taking place. So we have questions today. The universe is open or closed. Another way of saying that, there's this parameter omega, which is the actual density relative to a critical density. The critical density is the one that decides whether the universe is open or closed. If there's a lot of matter, it's closed. If it's not too much matter, it's open. If you're at critical density, it's sort of flat. It appears the universe is very close to being flat, and you can ask why, because that's a very, very special condition. And if it were any different, either the universe would have just diluted itself out, emptied itself out through the expansion, or was so dense that it would all have collapsed and everything would form black holes, and there wouldn't be anything left anyway. So you could then say, well, there's a principle, it's called the anthropic principle, and that says, well, we're biased observers. The only measurement we can make is one where the universe is basically flat, where this omega is equal to 1. Because in any other universe, it wouldn't have the conditions to promote life, and we wouldn't be there to ask the question. So we will always measure it to be that way. It's not a very scientific theory in my view, but a lot of scientists were promoting it, and in some contexts still promote it. Not this context. This crops up again and again. Another question you can ask is, why is the universe so isotropic and homogeneous? That doesn't have to be that way. You don't need that for making, well, it depends on how much inhomogeneity you put in. But it does appear that the universe is 3 degrees everywhere, as I showed a little earlier. And what really interested Guth at the time was this grand unified phase transition. And the phase transition, one of the products of the phase transition is the production of what are called magnetic monopoles. Okay, you might wonder, what is that? Most magnets that you have, well, all magnets that you have, I should say, come with a north and a south pole. Right? You're not going to find another one, I can assure you. But if you want, for fun, go to your hardware store and ask the salesperson there, can you have a dozen north poles? And just see how he looks at you. Well, okay. In principle, you could have just isolated north poles and isolated south poles. Those are called monopoles, right? But we don't see any. But they are produced in that grand unified phase transition. Actually, it was predicted a lot of them would have been produced. So inflation is a theory that was developed actually really to get rid of these monopoles, because you blow up the universe, you dilute the number of monopoles away to almost zero, so we don't find them. And it was based on this idea of a cosmological phase transition. You're dominated by the vacuum, so you get this exponential expansion. And as a byproduct, and this came a year or 2 years later, that if you really do the calculation of how this transition happens, you find that there are actually fluctuations, these little ripples that I mentioned early on, these quantum fluctuations, which are calculable, and they will eventually lead to density perturbations, which show up in the microwave background. Even better than that, the actual form of these fluctuations is what is actually seen in the microwave background. So it's not a proof of inflation, but it's telling you we might very well be on the right track, and I'll come back to that again a little bit later. So it solves all these cosmological problems, and as I say, it's testable. So that, we're still here now at 10 to the minus 36 seconds. But more happened then. There's a lot to work on at that time. Another question, important question in cosmology, is where is all the antimatter? So I'll tell you what antimatter is in a second, but so you need to know first what is antimatter, and then where it is, and then again we'll have the role of grand unification. So when Dirac was trying to formulate a quantum theory of special relativity, he found that you needed to have some extra particles which had all identical properties except the quantum numbers were flipped. So for the electron, he said, well, the electron by itself doesn't make any sense in the theory. You need to have a partner to that, which is called a positron. It's identical in all respects, but the charge is opposite. And all particles, almost all particles, have antiparticles. A proton, which is made of 3 quarks, a U, U, and a D. Don't have to worry about the nomenclature, but it has an antiparticle called an antiproton. A pion made of a quark and an antiquark has its antiparticle, pi plus, has a pi minus. There are neutral particles that can have antiparticles. The kaon is a different combination of quark and antiquark. It has an antiparticle. Neutrinos have antiparticles. The photon, gamma here, the photon is its own antiparticle. Pi 0, which is like a UU bar or a DD bar, is its own antiparticle as well. So this is not, again, this is not some theoretical construct. This is something that's, after it was predicted, it was observed in nature. It was observed in cosmic ray collisions. So particles streaming down on the atmosphere of the Earth have collisions with our atmosphere, and these antiparticles were observed. You can, of course, produce them in accelerators at will. The theory, the Standard Model, among the particles, so beyond the electrons and the quarks, there are special particles, the photon is one, which are the force carriers. So we had the electromagnetic force, the weak force, the strong force, and gravity. Each of the forces has a particle which carries the information about the force. So for the electromagnetic interaction, it's the photon. For the weak force are 3 particles called W and Z. The strong force has 8 particles. They're all called gluons. They're slightly different in nature, and gravity has a particle called a graviton. When you go to a grand unified theory, you get more symmetry, more forces if you want, and you get new particles which have typically been called X and Y. These X and Y particles are important because now they will violate something called baryon number. And what baryon number is just a term for particles that are made of 3 quarks. And you need to violate this because you need to change the baryon number or the number of protons relative to antiprotons. And why is this important? And why is this violation important? Well, if you think about electric charge is conserved. We've never seen any interaction at all ever that violates electric charge. And because of that, the electron is stable. Most particles, almost all the particles that we know of, are not stable. The electron is stable because there is no lighter particle with charge. So it has nothing to decay to if charge is conserved. As far as we know, the proton is stable as well. And that's because the proton is the lightest baryon. And if baryon number is conserved, there's nothing for the proton to decay to. Now, in a grand unified theory, that's no longer true. Baryon number is not conserved, and in principle, the proton should decay. And that becomes a key test of how you can understand or prove the existence of grand unification. And for many, many years, there was an experiment up in northern Minnesota in the Sudan mine looking precisely for proton decay. Unfortunately, it has never been discovered. So what does proton decay look like? Well, let's back up and just take a quick example of a neutron decaying. So again, something very well established. It decays through the weak force. So you have a neutron made up of 3 quarks going to a proton of 3 quarks. So baryon number doesn't change because it's 1 for each of them. They're both made of 3 quarks. But the neutron will decay to a proton and an electron and an antineutrino. Electric charge is conserved, 0 on the left, +1, -1 on the right. And you can calculate its lifetime. It has to do with the mass of the W, and it's about 10 minutes, and that all comes out very accurately, and it's great, very well understood. So something similar happens for the proton in a grand unified theory, but now it exchanges one of these X particles. But these X's are really, really heavy. So that's why we've never been able to produce them. And you see the lifetime here is about 10 to the 32 years, the prediction. Now, you can think about that a little bit too, because I told you the universe is, again, 13 billion years. That's 10 to the 10. This is 10 to the 32. And I said there was experiments looking for this. And you can ask, how are you going to find something with a lifetime of 10 to the 32 years when the age of the universe is 10 to the 10? Okay. Good. Now we can start moving to, a lot happened in that first 10 to the minus 36 seconds. Okay, it took me a lot longer than 10 to the minus 36 seconds to tell you about it. So there's a lot of other things that happened that I won't really tell you about. At 10 to the minus 10 seconds, that's a tenth of a microsecond. You had other phase transitions happening. You had the electroweak interaction breaking down into separate weak and electromagnetic forces. A little bit later, a tenth of a millisecond, you had transition from the universe being filled with quarks to hadrons. Okay, so that gets us from 10 to the minus 10 to 10 minus 4. Now we're going to jump to about 100 seconds. And that's the epoch of nucleosynthesis. And that came largely from the work. So all of Big Bang cosmology grew out of this idea that Gamow and Alpher, which is his graduate student, and Herman, his research associate, had to try and understand the origins of the elements. And to do that, they said, well, they came up with a theory that was consistent with relativity, but it also then predicted the existence of this microwave background at 3 degrees. Actually, that really was the work of Alpher and Herman. Alpher went to his advisor, George Gamow, and said, you know, the theory we're working on, there's a prediction that there should be some leftover radiation at 3 degrees. And Gamow got very angry. He said, nobody's going to ever discover such a thing. Stop wasting your time. And then, of course, it was discovered some 16 years later. So here's Gamow, Alpher, and Herman. A lot of times it's associated instead with Alpher, Beta, and Gamow. These are real people. Beta is, of course, the renowned theorist. I won't tell you the story behind this, but if you ask later, I'll be happy to. There's a nice story about it. It actually went farther. Gamow had a great sense of humor. He wanted Hermann, who's not here, to change his name to Delter. So they were trying to understand the table of elements. It's now known, of course, that Big Bang nucleosynthesis doesn't account for this. It accounts only for hydrogen, helium, and lithium. Beryllium and boron there are also highlighted, but they come from cosmic rays, not from the Big Bang. And everything else comes from stars, or something related to stars. So people grew weary. They said, okay, it doesn't work. The Big Bang nucleosynthesis doesn't work. And so they sort of dropped it, went off and developed stellar nucleosynthesis, which was very important and really gave us the understanding of really where all the elements do come from stars. But there were some problems that got left over. There's a lot of helium in the universe. About 25% of the mass of normal stuff is made of helium-4. There's also some deuterium around, that's heavy hydrogen. And nothing else can account for that. And so people went back to look at nucleosynthesis. So we're going to move along. After that's 100 seconds or so. So this is the work of Alpher and Hermann. This is a little bit more technical, but I just wanted to point out, they did this calculation. This is in 1948, you see. And you don't have to worry about all the things. There's some amusing things in what they've written here. The number there is 5 degrees Kelvin. That was their prediction. They said, it's 5 degrees Kelvin. They said, well, we're not 100% sure about that. It's sensitive to some things. Maybe it's 1 degree Kelvin. So in 1948, they predicted between 1 degrees and 5 degrees. Okay, amazing. And then we jump to 1964. Penzias and Wilson at Bell Laboratories were trying to perfect a radio antenna. They had a bunch of noise. They couldn't get rid of it. And it corresponded to what's called an antenna temperature of about 3.5 plus or minus 1, right in the middle of what Alpher and Hermann predicted. Now, Penzias and Wilson didn't actually know this. It was the people next door at Princeton, the theorists there, that recognized immediately what this was. And this field developed very rapidly. And this is a picture of the COBE satellite from the 1990s. Which really established the nature of this microwave background to be a perfect black body. And you see now how it's measured. It's 2.7255 plus or minus 0.0. This is the most perfect black. You can't make a black body like this in the laboratory. The curve there is not just a fit to these boxes. That's a theoretical curve. That's an equation. All it depends on is the temperature, and you get that curve. And it matches their data, which probably means that their boxes, which represent the errors, are probably too large. So we have Penzias and Wilson that just saw a uniform temperature. Then you have COBE. There you see again the galaxy. But what they saw is now temperature differences in the sky. It was the first indication that these fluctuations really were there. We knew that they had to be there, but now that they were actually visible. MAP, later called WMAP for Wilkinson, saw it in much, much finer resolution. And then you get to Planck, which was a satellite that went up a little over 10 years ago, about 15 years ago, I guess. And that's their map of the sky. And the plot here, to me, this is one of the most amazing plots in cosmology. This is a plot of the fluctuation spectrum. This is telling you about differences in temperature across the sky at different angles. So if you look at small angles or if you look at big angles, small angles are to the right, big angles are to the left. There's some scatter at the left because at big angles you have much less sampling that you can do. But on the right, you have very good statistics. The curve there, again, is not just a line drawn through the points. That's a theoretical curve based on 6 quantities. Okay? It has to do with the overall curvature of the universe. It has to do with the spectrum of fluctuations there and some other parameters that I don't need to go into here. But based on those 6, you get this shape. And to me, this is amazing how it goes through, the theory goes right through the data once you fit these 6 parameters. This is really astounding. This work is this kind of work is also going on here. We have in the physics department, we have and in the Institute for Astrophysics, Shaul Hanani and Clem Pryke, who are taking this stuff all a bit further and into the next level. The implications from Planck are, as I said, it tells you something about the curvature and it tells you something about the spectrum of these fluctuations. And these things were predicted, right? These things were known back in the 80s, and now only now we see what they are, and they are in some sense a kind of confirmation of this idea of what happened at 10 to the minus 36 seconds. Okay. They also tell you something about what the universe is made of. So here is, well, this is the same omega as the fraction of critical density for matter, for dark energy if you want, on the vertical axis. And so you get this split where it seems that most of the universe now is in this form of dark energy. I haven't told you what it was yet, but it's the thing that's driving this accelerated expansion. Another quarter of it is in dark matter, and about 5% is what we're made of. So it's very unsatisfying that we really only understand about 5% of what makes up the universe. But that's the way it is, and that's the way it is today. So the dark energy, I mentioned this cosmological constant. That was what Einstein introduced to get rid of the expansion. And when he found that the universe is expanding, he said this was, his biggest blunder. But yeah, maybe it was just another stroke of genius. Einstein was full of strokes of geniuses. I mean, it's amazing he only got 1 Nobel Prize. He should have had at least 5, if you count. But this number, so it could be that this dark energy is just another cosmological constant. There's no reason that it can't be what Einstein predicted back in the early parts of the 20th century. Problem is that it's really a small number. In some kind of dimensionless unit, it's 10 to the minus 121. That's really, really a small number. And nobody has a real good idea of why that's the number. So there's still a lot of thought, a lot of room to have further understanding of what's going on. Whether it's this or whether it's some other form of dark energy, we don't know. We don't understand it. It appears to be there, but it's consistent with this cosmological constant. By the way, this brings back the anthropic principle, because people say, well, it could have had any value, but in all the universes where the value is much bigger than this, we wouldn't be here to measure it, which sounds very reminiscent of what was going on for inflation. It actually went on for that matter-antimatter asymmetry. People were using anthropic principle as an excuse, which works until you have a better solution. So we're almost at the end here. We got up through the microwave background, and then, of course, what happens then? The universe develops neutral matter. We go into the dark ages. These fluctuations that were produced by inflation start to grow. They eventually form dwarf galaxies, and that eventually leads to galaxy clusters. And of course, you have the first stars being born along the way as well. So I'm going to leave you with that. So here's our plot. We've seen this many times. Hopefully, you have a better appreciation of what's in the plot now. You see all sorts of particles early on. Eventually, the number of particles dwindles down, at least the number of free particles. You get groups of particles forming, and eventually you get to where we are today. So I'll stop there.
So it's time for 3 questions. Please wait for the microphone. Any questions? There's one.
Weren't you going to tell us why some stars are 15 billion years old?
Oh, I didn't say there. I said the distance to the star was 18 billion light years away. That's not the same thing. So you're asking, why is that the case? It has to do, again, with the notion of a geodesic. And the distance light travels is not related, well, it is related directly, but is not just equal to the age of the universe, or the age for where it was born. See, the universe is expanding. So even if we live, I said the universe is flat, that's spatially flat. It's not flat in space-time. The universe is expanding. Things that we see now as very far away, in the distant past, they were, of course, much closer to us. So in a universe, well, if we were matter-dominated, it's easier to say. Now we're, again, getting to be like vacuum-dominated, but let's say we were matter-dominated. The actual distance light travels is about 3 times the age of the universe. It doesn't violate anything. It's completely consistent with special relativity, with general relativity. It just has to do with the fact that the universe is curved. So 18 billion years, light years away is fine. It doesn't mean it was born 18 billion years ago.
Question? Yes,
I think there's...
So can you hear me?
Yeah.
So what about the possibility that the universe expands and contracts?
Okay, so it's part of the set of solutions. So it doesn't appear that that's the way we're heading, but in a closed universe, that's typically what would happen, that the universe would expand, reach a maximum, and then recollapse. Okay, that's one of the standard classical solutions. It can also happen in an open universe with a negative cosmological constant, so that's another possibility. You can have it expand for a while, and this is an infinite universe, and then still recollapse. It appears that that's not where we're heading. It appears that the makeup of the universe, especially now that all this dark energy or the cosmological constant is present and is dominating, looks like it's going to drive us to an expansion that's going to last, unless something else that we really don't understand in the very, very distant future, we're going to be expanding forever and faster, and we will eventually not see any. We see more stuff as the universe gets older. If this accelerated expansion happens, that will stop. We will just be left with what we see. I mean, it's still very big, as you see, but that's it. We will be sort of a little island in this vast expansion.
There was a question there.
There's one over here.
And yeah, okay. I just wanted to also.
I'm closer to the mic.
Okay. So earlier you mentioned the graviton. Is that something that's widely accepted within the scientific community, or is that still theorized?
I would say it's widely accepted. Of course, now you have to be a little bit careful with the terminology. So a graviton as a particle, so now you have to be a little bit concerned about the quantum nature of the graviton, as opposed to the wave-like nature of the graviton. So a photon, the carrier of electromagnetic interactions, will appear both as a wave, electromagnetic wave, or as a particle that you can do a scattering experiment with. Quantum mechanics will relate those two things. The graviton as a wave is now absolutely firmly established because the gravitational waves have been discovered some 9 years ago, and those experiments are going on. There's Vuk Mandik here, who's part of that set of experiments that are continuously looking for gravitational waves, seeing collisions of black holes, collisions of neutron stars, fascinating stuff. So that aspect of the graviton is the way we think about it is it's a perturbation of a gravitational background. So you make a little bit of a fluctuation, and the wave-like part of that fluctuation has been established. The particle-like part has not been established, but I don't think anybody really doubts that there is still this kind of duality.
There was a person here in front.
I have a mic here.
But then we have to go.
Question about the unifying theory of gravity with the smaller forces. Where are we at with the progression of that and understanding of that? Do you see that being actually, getting somewhere in our lifetime?
Well, it depends whose lifetime. So in the 70s, late 70s, there was a lot of excitement because and you had all these proton decay. So one of the first predictions is that protons are unstable. And you make an experiment, you look for protons decaying. And as I said, there was an experiment here in Minnesota. There was one outside Cleveland, in Japan. There were in India. There were a number of these experiments. None of them found anything. Now, as I said, it's very sensitive to that unification scale or the unification mass. You push it up a little bit, the lifetime grows enormously. A factor of 10 higher in the mass, factor of 10,000 times in a lifetime. And if you're expecting like one event a year, and all of a sudden you get one event every 10,000 years, that's sort of rough, unless you make even bigger detectors. But that's not the only prediction. So there are other predictions for grand unified theories which involve things like baryon number violation or something related to that, which is called lepton number violation. It has to do with the sector of the theory that involves electrons and neutrinos. So there are experiments that look for neutrons oscillating to antineutrons. There are things that are looking for certain nuclear reactions which don't emit neutrinos, where normally they should. So there are still a lot of experiments going on, but if you ask me the probability that it's going to happen anytime soon, I don't know. That's anybody's guess. There are a lot of people looking for it. It's extremely important. Of course, there's a chance, but beyond that, I don't know. I mean, we don't know at what scale this actually takes place. Is it at 10 to the minus 34 seconds or 10 to the minus 37 seconds? I mean, we know it's around there, but we don't know more. We need the experimental information.
In the start of lecture was about the beginning of time. Before was time, before the beginning of time.
Okay, so it's a normal question. It's a normal question. Where did the time come from? So if the universe didn't start at a particular time, right? Because time itself was created with the universe. So, and this is a hard thing to understand, but it's also hard to understand how infinite space can be created. We're again talking about strictly the Big Bang theory coming from general relativity with no extra corrections, say, from string theory. So we don't separate in the theory between, not completely, we separate a little bit, but between space and time. There are just 4 different coordinates. They are treated a little bit differently, and we certainly perceive them differently. But we talk about the Big Bang creating space, it's also creating time. It's space and time. And at that moment is what we call the origin of time. Now, there are theories which say that we're actually eternally or perpetually in this sort of inflating state. And every so often you have a kind of transition that gets you out of it, and that would be the moment of the Big Bang. But now time and an origin of time only refers to the moment when our patch of the universe separates out from this global expansion.
If I'm not mistaken, it is hypothesis that before the bang, there was something kind of black hole. It's some matter or space.
No, there's no center. There's nothing. Again, there's no place that this happened. It happened everywhere, and that's when the time, what we call time, was created as well. But again, that's probably taking relativity beyond its limit of validity.
Thank you.
Questions?
Yeah, thank you. So you described a phase transition where between different vacuous states, and that potential was changing, I guess, with time.
There it was with temperature.
Oh, with temperature, okay. So is it possible that that potential would be fixed, and just at high temperature, the particles would just not notice this little dip on the side?
I mean, in the picture that I showed, the idea here is that at very high temperatures, the symmetry is restored. So there's only one minimum at high temperatures, and so you're forced to be in that particular vacuum state at high temperatures. As the universe cools, then another minimum becomes available. So if you start with steam, right, if you're at very high temperatures, you're going to be in the steam phase. And as you cool, eventually you're going to condense out and get droplets of water because there's a lower energy state for the material. And here, the bump there, it doesn't have to be a bump. It could be nice and smooth, but if there's a bump there, you can lead to, in terms of material phase transitions, would be like a supercooled state where the material is not in the right place at the right temperature and really should be somewhere else.
Okay, so you're saying that that curve really does have to change. It couldn't just be fixed and...
Well, in general, it should change because the way you compute that curve, the curve itself at, say, 0 temperature is the basics of your theory, but then you have corrections to the theory at finite temperature, at high temperatures. So there will be corrections that you can compute.
Okay, one last question. This is getting late.
Hello?
Yep.
Yeah, so earlier on you teased us about a funny story. I don't remember if it was alpha, beta, and gamma or somebody else, but...
Yeah, it was the, these guys. So, as I said, Gamow had a great sense of humor, which displayed itself in numerous aspects of physics. But here, he knew, his student Alpher, he's Gamow, and Hans Bethe is a famous theorist, sort of working in somewhat closely related aspects. So, and this I know to be true because actually I was a graduate student and Bethe came to visit us at the University of Chicago, and we all asked him about this paper because it's obviously sort of amusing here. And he said, well, actually I didn't have anything to do with this paper. He said that Gamow sent him a copy of it. He read it. He said, I didn't see anything obviously wrong with it, and so I agreed to lend my name to it. These days that would be really frowned on as being unethical, but okay. So this was really a joke that Gamow wanted to promote. And as I said, I think I have it at the end here. So here was this is the paper. So this is also 1948, Alpha, Bethe, and Gamow in the Physical Review. And there's a footnote in a paper by Gamow. He said, the atomic species recently developed by Alpha, Bethe, Gamow, and Delta. That paper never existed. Hermann did not agree to change his name to Delta.